Here we have the same instructions that we had in the previous example, but the function is going to be different. Our instructions are to approximate f as indicated, use Taylor's inequality to estimate the accuracy, and graph r sub n, the remainder function. In this case, our function is f of x is equal to the natural log of the quantity of 1 plus 2x. A is equal to 1. N is equal to 3, meaning find the third degree Taylor polynomial. And the interval we're given is x goes from 1/2 to 1.5. I would first like for you to pause the video and find t sub 3 for f of x is equal to the natural log of 1 plus 2x. All right, so for the function f of x is equal to the natural log of 1 plus 2x, the first derivative is 2 over 1 plus 2x. Don't forget that we are going to have a chain rule at every step here when we take derivatives. So f double prime is 4 over 1 plus 2x squared with a negative in front because the exponent in the previous derivative was -1. F triple prime is 16 over 1 plus 2x, the quantity cubed. Evaluating those for a equals 1, f of 1 is natural log of 3, f prime of 1 is 2/3, f double prime of 1 is -4/9, f triple prime of 1 is 16 over 27. I should note here that our values were n equals 0, n equals 1, n equals 2, and n equals 3. That's what we need for t sub 3, the third degree Taylor polynomial. However, thinking ahead, we know we're going to be using Taylor's inequality, and Taylor's inequality involves the n plus first derivative. And so I've gone ahead and computed the fourth derivative of x at this stage here. And that result is -96 over 1 plus 2x, the quantity to the fourth power. We don't need that for Taylor's third degree polynomial, for the third degree Taylor polynomial, and so we'll just come back to that later. Using the coefficients that we got from evaluating the function and its derivatives at a equals 1, we have that t sub 3 of x is the natural log of 3 plus 2/3 times the quantity of x minus 1 minus 4 over 9 times 2 factorial, that's the denominator, x minus 1, the quantity squared, plus 16 over the quantity of 27 times 3 factorial times x minus 1, the quantity cubed. Remember that 2 factorial and the 3 factorial are coming from our expression for ci that we saw in previous work. You may be looking at this saying, this isn't a polynomial because there's a natural log in it. Not true. It's true there's a natural log in it, but it's the natural log of 3. That is a constant. For where the variable appears, there are only positive whole number exponents, and that's a requirement for us to have a polynomial. These simplify so that t sub 3 of x then becomes the natural log of 3 plus 2/3 times the quantity of x minus 1 minus 2/9 times the quantity of x minus 1 squared plus 8 over 81 times x minus 1, the quantity cubed. That answers part A. For part B, to use Taylor's inequality, we need a couple of things. We need m, and we need an expression that looks like x minus a in absolute value is less than or equal to d. For m, we go to the fourth derivative. Remember that the fourth derivative was -96 over 1 plus 2x to the fourth power. And I'm just going to copy and paste that down here. The interval that we were originally given, I'm going to write it down here because we're going to need it in a couple of different ways, is that x was supposed to go from 1/2 to 1.5, and don't forget that a is 1. So x went from 1/2 to 1.5 with a equals 1. Okay, on that interval from 1/2 to 1.5, we need to determine the largest value that the fourth derivative will take on. If we look at this, what we can see is that our fourth derivative is negative. and we have a 1 plus 2x, the quantity to the fourth power, in the denominator. And I just about sent us down a wrong road there. We don't care that the fourth derivative is negative because we are considering the absolute value of the n plus first derivative. What we do care about is that if x is smaller, then the denominator is smaller and the overall expression will be larger. If x is bigger, because it appears in the denominator will be bigger, the overall expression will be smaller. Therefore, since the absolute value of the fourth derivative is larger for smaller values of x, we're going to use x equals 1/2 the smaller endpoint. So the statement that we're actually making is that the absolute value of the fourth derivative of f of x is less than or equal to the absolute value of the fourth derivative of f at 0.5. That's what we're going to use for our m. Some quick arithmetic will tell us that m is equal to 6. Now we're going to use the original interval, x going from 1/2 to 1.5, and a equals 1. Remember, we want to get the expression x minus a in absolute value is less than or equal to d. Subtracting 1, because a is 1, from all three parts of this inequality is going to give me negative 1/2 is less than or equal to x minus 1, which is less than or equal to 1/2. Therefore, we can say that the absolute value of x minus 1 is less than or equal to 1/2, using a technique that or a thought process that we saw before. We can now put this together. We can say that in magnitude, r sub 3 of x is less than or equal to 6 from the m divided by 4 factorial, that's n plus 1 factorial. And since x minus 1 in absolute value is less than or equal to 0.5, we're going to use that 0.5 to the fourth power in place of our x minus a in absolute value to the n plus 1 is approximately 0.015625. For part C, we're supposed to graph r sub 3 of x in absolute value, and remember that that equals f of x minus t sub 3 of x in absolute value. F of x was our original function, the natural log of 1 plus 2x, and t sub 3 is what we just found, so this is from above. It should be no surprise to you that I have graphed this here. And what we see is y is equal to the absolute value of the natural log of 1 plus 2x minus the third degree Taylor polynomial. You can't see it all, but I swear I typed it. The purple curve is r sub 3 of x, and the vertical blue line is where x equals 1/2. The vertical black line is where x equals 1.5, because that was our original interval. And what we see is there's a larger error on the left than on the right. I care less about that. Also, there's almost no error when x is 1, and that was the center, right? A was equal to 1. We want to estimate the maximum error by looking at the graph, and so I'm going to look over here at the left, and what I see here is where the purple curve intersects the blue vertical line, that value is actually less than 0.005. And it looks like it might be close to 0.004, a little bit bigger than that. Here's the thing. We found from Taylor's inequality that the error should be no more than 0.015625. The actual error is less than 0.005. And so the graph gives us a greater idea of what the accuracy is, but what we can see is that Taylor's inequality still holds. Now we might look and say, well, look, Taylor's inequality is wrong because here it's closer to 0.005. It's not true. It's true that it's closer to 0.005, yes, but it's an inequality. And 0.005 is indeed less than the number that we came up with from the calculator.